this operator. Hopefully that makes sense. Okay. And then the 3D Greens function example, all we're going to do is compute the responses at a set of points due to both strike slip and reverse slip on the fault. And to do this, we'll need several different config files, which you have your main pilot app.config file, which is used by all of the examples in 3D Hex 8. Then we have a specific greensfunctions.config file, which are the settings that are specific for greens functions. And then we have the one that's very specific to this example, which is step21.config. And we'll look at all of these files when we're going through the 3D example. And then when we run this, all we have to do is type pilot, but then we're changing the problem type to Greens function. So you then have to type pilot -- problem equals pilot.problems.greens functions. And then you give it the step21 config, which is the specific parameter file for this example. So to start with, I'm just going to go very quickly through the mesh generation for the 2D Greens function example. So okay, hopefully everybody can see Qubit now. And I'm in the reverse fault example. So again, we have our top level file, which is mesh_try3.journal. And it in turn is going to call a few other journal files. There's the geometry file. There's a gradient.journal file. And what this does, it uses Qubit's bias sizing function to allow us to vary the size of the mesh. Then we're going to mesh the entire thing, and then we'll create our boundary conditions. And again, I don't want to spend too much time. We'll go very quickly. I've already set my directory correctly. Again, we're going to use apropos to do our to take care of our variables. We're going to create a block. We're going to put a fault in there. And let's see, I haven't gone completely through this. Anyway, let me go ahead and start from this. So we'll go ahead, start by creating our block. Okay, not particularly interesting. Okay, create mid-surface volume. Have to see what this is.
Creating the mid-surface just chops the block, takes a slice through the block to create a 2D rather than building up points and curves.
Okay, so we've chopped the block along the plane, and yeah. Okay, and then we're going to create a fault just by specifying some positions and splitting the curve. So here we have so that's going to be, I believe, probably the coseismic part. Then we imprint and merge everything. Oh, well, we don't have enough volumes for that to do anything. So we've done that. Then the gradient. This one is a little more interesting, where what we do is we're using apropos, and we're setting a bias factor. This is similar to the 2D subduction problem we did yesterday. So we're going to just set some variables here. Setting some, there we go.
Charles, you need to go back to your mesh file. You missed some commands before the gradient.
I did. Okay, what I'll do, I'll just start this whole thing from here. We'll play the geometry. Yeah. So we'll start all over. We go to gradient. Okay. Then we're going to put no sizing function at all on any of the curves. And then we'll put a constant size on the fault surface, so we can see what we've done. So we've just put constant mesh size on that part. And then we're going to do some bias curves. Okay, so we can look again. So that's the type of mesh sizes that we're looking at. Set a constant size on there. I'm just going to finish setting the rest of these sizes.
So the question is, Charles, is the purpose of the bias curve to create a finer mesh on a particular portion of the fault?
Yes, that's true. What we're doing, we're interested, this part of the fault right here is where we're going to apply the fault slip. Let me just, what I want to do. Okay. So now, yeah, that particular curve, we want finer resolution. But then what you don't want to do is to abruptly change resolution as soon as you move away from your feature of interest. And so you can see on the rest of the fault extending down, you're gradually increasing the mesh size. So now that we've done that, we've done the gradient part, we're going to just mesh the whole thing. There we go. And so you see we have a mesh that's pretty fine right around the fault where we're interested, and then kind of decreases as you move away from there. And we'll take one pass at improving the mesh quality, which happened pretty fast. Okay. And then there's just the boundary conditions. And these are pretty standard. I don't think we're doing anything that we didn't cover in the meshing sample. So I'm just going to play those from here. Okay. And if we look at our boundary conditions, we have our blocks, which is just a single block. It's the whole thing. Our node sets, we have there's, I don't know if you can see it. There's the fault. Doesn't show up very well. And then just our regular, oh, actually, let me just do it. I'll show it better that way. Yeah, it's just our regular node sets. So we've created our mesh, and now the next phase is to generate our fake data. So to do that, okay, I'm in you can see I'm in the 2D greens functions reverse directory. So if we look at the files in there, we have we've just generated our mesh, which is, oh wait, I didn't finish doing that. I'll just do it for good luck. You won't see it, but I'll okay, I just regenerated the mesh. We have our config files. So the pilot that config file is just fairly standard. We have our regular journaling stuff. This is a qubit mesh. Here's our file name that we'll use for everything. We're reordering the cells and vertices. This is just a kind of an optimization thing. This is a two-dimensional problem that we're solving. We're using kilometer for our length scale normalizer. Our time steps will be in seconds, although it doesn't really matter since this is a static problem. Then we have our time step size, which is a year. So we have just a single elastic material, so it's elastic plane strain. We have a single block that we created in qubit, so it has an ID of 1. This is where our material properties are defined. We can look at that. It's just our elastic properties. This is triangular cell, so this is fiat simplex type of element. Our cell dimension is 2, since it's a two-dimensional problem. We're using extremely simple boundary conditions. We're just putting zero displacement boundary conditions on the x negative, x positive, and y negative edges of the mesh. So on the x positive edge, we fix the x degree of freedom. On the x negative, we do the same thing. And then on the y negative, we just fix the y degree of freedom. We have a single fault. So we create an array with just one entry, which is we're calling fault. And so we have an ID of 100. We're giving a label of fault. And then this is also our integration information for the fault. You drop down one dimension. So this is, again, fiat simplex, but in this case, our cell dimension is 1. Now, we're going to include one new thing that we haven't seen yet. For this type of problem, in addition to having output over the entire domain and over a subdomain, which is just the ground surface, we're also going to output the solution at a set of points. And this is the output solution points right here. So we have, you can see our output. We have our domain, which is just regular output over the entire domain. Ground surface, which is a subset of the domain. So this will just be a line along the top of the mesh. And then points. But right now, we don't know which points those are. So for the domain, we're going to use HDF5 output, the output to a HDF5 mesh. For ground surface, we have to tell it what the label is. So we're outputting over face ypos, which is a node set that we defined in Qubit. And this is HDF5 submesh output. And then finally, our output for the points. In this case, we have to tell it the spatial dimension for the coordinate system. It's 2. The units, we're using kilometers for our coordinate system units. It's, again, HDF5 mesh output. But we have to tell it where those points are, and we're doing that in this extra file, which is called output points.txt. So we can, the rest of it is just output for the fault and for our for the state variables. So if we look at this is the points where we're going to compute our solutions. So these units are in kilometers because we said that in our config file. And so it's just a set of points. They're all at y equals 0, which is the ground surface for this problem. So the other thing that we have our eqsim.config file. And this is specific for the forward simulation. So this is what we're going to do to create our fake data. So we have a fault cohesive kinetic for the fault type. And then we're going to specify the slip on the fault in this spatial database. We're going to do linear interpolation for the slip. And then we just give a label to the slip. And then the slip time, this is a static problem, so it doesn't really matter. So we're just uniform database, slip time, and we slip at t equals 0. And then we have our output for the simulated earthquake. Just this is our eqsim.h5 for the entire domain output. For the ground surface, we've given it this file name. Then for our point output, we're giving it the points name here. And then we also output our fault information here. And then finally, things like stress and strain will be in our state variables output. If we look at the spatial databases that we're using, for 2D problems, we only have, along the fault direction, we only have one component of slip, which we're calling left lateral. And we're going to specify the slip at 4 locations. The data dimension is 1, since we're specifying the slip variation along the line. The space dimension for our problem is 2. And we're going to, for convenience, specify our coordinates in kilometers. So then when we come down here, we have we're just specifying it in terms of a vertical variation. So starting way up in the air, we have slip of minus 2.5 meters. And that goes down to 12 kilometers depth. We have 2.5 meters of slip. And then going to 15 kilometers depth, we all of a sudden drop to 0 slip. And then continue 0 slip all the way down through the bottom of the mesh. Now our material properties, I believe we've kept those constant. Yep. So we just have a single location, so data dimension of 0, and we're using just single values for EP, BS, and density. So all of this is described in the README file that's one level up. So you can see what the steps that you need to do. We've generated the mesh, and then we're going to run our forward simulation. So to do that, we just looked at eqsim.config file. So we'll just run this problem. For some reason it's taking a minute. Oh, there we go. Okay. Okay, so we ran our problem. All of our output is in the output directory. So we've created our simulated data. Of particular interest is the point data. So what I might do, just look really quick. Actually, what do I have, 45 minutes for this? I think.
Set a total of an hour for the 2D one.
Oh, okay, good. Okay.
But you got to do the greens function.
Yeah, I just wanted to look really quick. Oh, not there. I was going to show. This just shows the slip that we've applied on the fault. So you can see for our fake problem, 2.5 meters of slip here, and then we'll just see what that did for the ground surface. Okay. Wait, is that right? Let's see. Okay. And then the other thing that we've done is created output at a set of points that we've defined. I'm going to turn off the ground surface, and I'm going to make the points bigger. So what you can see, that's what I'm saying. We've computed the solution now at this set of points, and this is what we're going to use for our inversion. Yeah, there we go. All right, so getting back to our steps. So we've done that. Now we want to generate our greens functions, and the ingredients for doing that. First of all, we have our greensfunctions.config file. So there's not a lot in there. We're giving it what our fault ID is, which we had in our pilot app.config file, I believe. And then we've changed the fault interface condition to fault cohesive impulses. And this is a specific type of interface which goes through all of the vertices on the point, on the fault, and applies an impulse along those for which you get specified non-zero slip in the spatial database, and then it'll compute the response at wherever you tell it for all of those. So we just have one degree of freedom that we use, and this 0 means left lateral slip. The amplitude of the slip impulses is given in this file right here. Or no, sorry, this file. Impulse amplitude.spatialDB. And we're going to use nearest neighbor interpolation, so it just gets the values at points. And then finally, for our output, we're going to give it the prefix of greens functions for all of our output files. So if we look at that file, you'll see it's pretty simple. It's just a single value, which is just slip. We're giving it in units, and we're going to do 2 locations, meaning basically everything, the entire fault, we're going to compute the slip on it. So, and then we're going to use, this is the slip amplitude, which is going to be -1 meter. So to do this, to run this simulation, or to generate the greens functions, all we have to do you'll see it has to solve a bunch of elastic problems to do this. It's almost as though it's doing a time-dependent problem, because it's computing a separate problem for each vertex on the fault. Okay, so now we've generated those. We look now. I'm going to delete some of these. We'll open the greens functions on the fault, and we'll open up the points. So again, we'll make them a little bigger so we can see. And we'll do the same with this. Okay, so now if you look at this, we actually have what looks like a time-dependent problem. I'm going to maybe we'll do the displacement X is fine. I'm going to scale that down a bit so we can see it better. Okay, and similarly for the fault. So what we've done for each vertex on the fault, let's see what happens if I do that. It doesn't really work. we create an impulse, and then we're creating what the surface displacement is at each of these points. So you can actually step through and see this is what we've applied, and this is what the response of the ground surface is. So as you start going through, you can start seeing how the response is different depending on where on the fault we're applying the slip. And of course, as you go deeper, the surface response is less and less. Now you'll notice also that it's not always in order. So we'll have to take that into account when we do our post-processing. So the next thing to do, now we've done that, looking back at our directions. Now we're going to do our inversion. So we'll look at the Python code where we do that. That's this. Now, I don't really have enough time to completely go through this. The important thing, the packages that we're using, NumPy and H5Py, which allows us to read the HDF5 output produced by Pilot. So we have what we do first of all is define a couple of functions that we need in the main part of the code. The first part gets both the impulse and response coordinates and values. And then we're going to sort those along the y dimension of the fault. So this is the impulses. So we've already, on our command line, we're going to give it what the name of the impulse file is. And then it opens up the HDF5 file, and it can get the coordinates of the impulses as well as the fields, which in this case is the applied slip. Now, I won't go by all of this, but one of the things that we do is we sort by the y coordinate. So that's what that function does. This one gets the our fake data, which we're getting from the EQSIM. And so that's another one that we're going to specify on the command line as our data file. We're going to open that. We're going to get the coordinates of the vertices, or which is the points where we've computed the displacement. And then we'll actually get the displacement values at those points. So here this is just a bunch of stuff where we parse the command line input and then get the values from the command line. Then we run our two functions. We get the impulse response information that we created when we generated our greens functions. This part, we're getting the data values, which is our fake data. And then we have penalty parameters. So we can look at the penalty file, which is this file right here. And that was the lambda that I showed you in our initial thing. And what you can see, we're just going up in powers of 10, where we gradually increase the weight assigned to our minimum moment solution. And then we have our number of parameters, which is the number of slip values that we're solving for. The number of observations is twice the number of data points, since we have both x and y displacements at each point. And then this is where we form our, well, I was calling it in the slide, I called it the G matrix, which is your main, is your coefficients that you multiply by the model parameters to get your data. Then we're going to create a diagonal matrix, which is just the identity matrix. And then that's going to be that's what's going to be our penalty parameter. Then we form our data vector, which is we take the data values and then we flatten those out so that we have all of the x displacements and then all of the y displacements at all of our data points, or at our observation points. And then the number of inversions that we're performing is equal to the number of penalty parameters that we're using. And so we create an empty array with our inversion results. And then we put our, let's see, okay. The inversion results is going to have both the coordinates and the computed or the estimated parameters in it. So the coordinates will be in the first two columns, and then the remaining columns will have the parameter values. Then we'll loop over the inversions that we're doing. Here we multiply the penalty parameter times our diagonal matrix for each inversion and form our augmented system of equations by stacking together our G matrix with our penalty matrix. And we need actually the transpose of this matrix, so we do that using NumPy. And then we form our generalized inverse, which is, that was shown on the presentation slides. And then our solution is just the multiplication, matrix vector multiplication of our generalized inverse times our augmented data vector. And then we fill up that column of our empty matrix here with the solution that we computed for that penalty parameter. And then we're going to compute the predicted results and the residual. And we'll print that output to standard output. Okay, so I'm going to just run through that. So to run it, I'm going to do exactly what it says here in the README. I don't know if I can, let's see if it will work all at once like that. Okay, so it did. So for each penalty parameter, it gave me what my residual norm is. And so that's just the norm of your predicted minus observed. And you can see that as we increase the penalty parameter, which means we're forcing the solution to be close to zero, we increase our norm. But what it also does, it gives us a smoother solution as we increase our penalty parameter. So that very quickly was the inversion. And then the final thing we're going to do, we want to, that didn't really tell us a lot. So what we want to do is look at the inversion results. And we've written another script called plot inverse results.py. And that will take the solution that we've computed with our inversion, which we've saved in this file right here. And then it'll compare it with the fake data, and it'll plot things up for us. So we'll just look really quickly. I want to go into reverse. Okay. Make that a little bigger. Okay, again, now the one additional package that we require for this is the matplotlib package. And we're going to import the package, but we're just going to, within the code, we can just call it this. So we're saying import this package, but within our code here, let us refer to it with this shortened way. So here we just define some things. We're defining the color of our solution plot, and then the colors for the various predictions. So this get solution function just opens up the true solution, which was the applied slip that we used in our simulation. And then it gets the coordinates and the slip values that we did and returns that. Again, we have some arguments that we bring in from the command line. So we have our solution file, and these are our predictions that we just did with our inversion. And then so we get our solution using the get solution function, which just reads in the HDF5 stuff. Then we load in our predicted fault slip from the inversion results that we just computed. We get the coordinates, and then we get the predicted fault slip. Then this is just some stuff that sets up our plot. We're giving it what the solution values are going to be for all of them, and giving it line width and a color for the plot. We're going to give it a label, and then the y-axis label, and then just the limits of the plot. And we're going to loop over the number of inversions that we've done. So for each inversion in the range of inversions, we're going to plot the predicted slip for that particular penalty parameter. And then finally, once we've gone over that, then we actually show the plot. So I'll just do that right now. Wait, I'll just do this. Wait a minute. Oh. Okay, so when we did that, we created this plot in Matplotlib. And so the horizontal axis here is the amount of slip, and then the true solution is shown here with the black curve, and then each of the solutions using the various penalty parameters are shown using the different colors of curves. And in general, what you find is this curve, these curves way down here will be the ones where we have a very high value of lambda, meaning that we really the solution is dominated by trying to stay close to zero. And then as the value of lambda is reduced, we start getting closer and closer to the solution, but we also get more variations in the solution here. So that's just a general characteristic of inverse problems. Now, I know in one of the exercises for the user, this is really simple, the minimum moment inverse. It's just forcing the solution to be close to zero. An exercise for the user would be to replace the diagonal with a penalty function which actually minimizes the roughness of the solution. And you can do that using a 1D Laplacian approximation. So to do that, you would have values of 1, -2, and 1 that are centered along the diagonal of your penalty matrix. So that, I believe, is pretty much the very quick run-through of the 2D Green's function example. And before I move along to the 3D example, do we have any questions? what they are, and how they are used. Well, HGF5 is a binary portable format that has a lot of nice features. One of them is that the files can look essentially like a directory structure. But they're also cross-platform, meaning that even though they're binary, you can take them from one machine to another, and even if you have a little Indian or big Indian machine, they're still accessible. They're also self-describing. And since they're binary, they're quick to write and quick to read. If you have...
Charles,
yes?
can you bring up my terminal and use the H5 dump to show what they look like?
Yeah, I forgot that I wasn't sharing my screen anymore. Can you see the X window here? Okay, so if we go to our output, and we'll look at output for the domain, for example, for the simulation. So this shows how an HGF5 file is arranged. So here's the top level. You see that we have and it's hierarchical. So we have our geometry, and within the geometry we have vertices. And then the vertices, you can see this is just giving indices to access the vertices, the actual coordinate values. Let's see. You keep, how many of those were there? There's like, were there 1,000 or more? Just scroll down. You should have the H5 dump command on your machine once you've installed Pilot. Okay, it has another one. There's time. This is very simple since there's a single time step. We have topology, which that's our cells. That just shows how the vertices are connected together. These are triangular cells, so each one is composed of three vertices. Should have looked how many. Might be quite a few. Let's see. Okay. Okay. Cell dimension is 2. And then we have our vertex fields, displacement. So this will be all of the fields that we computed at each node, at each vertex. So the one for points are going to be simpler. So here we just have a few simple vertices, XY coordinates, our time, and then, you know, topology for a 1D cell is pretty basic. Or 0D, because these are just points. And then we have the computed displacement of all of these. So what the Python script allows us to do is to access these in a pretty straightforward way.
Charles, can you do H5 dump dash lowercase n and then the file name so that they can see? That just shows the structure or hierarchy of the file.
Like
so that helps you identify what all the data sets and how they're laid out in the file.
So there you go. So we can do not much more in there. Yeah. So really, they all have very similar structure. Does that answer our questions? Okay.
We have another question. Does the type of boundary conditions matter here in the inversion?
Well, it depends on the type of problem you're solving. I mean, if you're looking at something like co-seismic fault slip, usually you don't want to superimpose on that like any kind of actual displacements at the boundaries. For co-seismic, what I found is that the most natural boundary condition is to constrain the degree of freedom perpendicular to the boundary. And so that's usually what we do for that type of problem. Now, if you were to include displacement field, then that signal is going to be included in any type of Green's function that you generate. But I don't think you would want that in there. Oh, yes. Yes, we can tell it all of the surface vertices. We can do, and actually we've done that. In the if I look at
I need to see your
we've
screen.
done it for did I stop sharing? Shoot, I keep forgetting. Okay, okay. So we've done it with the Green's function's ground surface. So we turn off the points here. We've actually we've computed it for the entire ground surface. So you can go back and just look at the response for the entire ground surface. Did that answer our question? Maybe I'll just leave my screen up here, so I keep forgetting otherwise.
So we have another question. How did you rotate the slip scale by 90 degrees?
Oh, all you do is you just bang it against the edge there until it rotates. You grab it and just, when you pull it up against the boundary, it rotates. But you could also, if I go to, say, this one, I believe you can edit that. Let's see. Maybe it's in here. No. Okay, I don't know if there's another, yeah, I don't know if there's another way of doing it other than just dragging it up against boundary, although it seems to me that there should be. Yeah. So that's the easy way to do it. You can just like that. Any more? Okay. Shall I move on to the 3D hexade example? It will actually be pretty quick because